Hello, everybody. It's Mr. Johansson, and we're going to be talking Earth Science lesson number 2, which is about observation and measurements, observation and inferences, and percent error and scientific notation. We'll just take you through these things pretty quickly, okay? So what's an observation? Well, it's any information directly obtained from our 5 senses. For example, identify which one of these senses is being used. Blue. How would you tell something's blue? Well, that's a sense of sight. How would you tell something's hot? You touch it, sense of touch. How would you tell something is salty? That would be the sense of taste, obviously. Incense. If somebody is burning incense, you walk into a room, how do you know? Well, you smell it. It would be your sense of smell. If you hear something loud, well, you're hearing. So that's your sense of hearing. Now, observations and instruments. We use instruments to extend our senses. For example, a telescope or microscope, what does that extend our sense of? Well, it would extend our sense of sight. How about a sensitive microphone? What does that extend our sense of? Hearing. A thermometer, remember that's touch. That's you tell if something's hot. So a thermometer extends your sense of touch. A meter stick, what does that do? Well, it extends, well, which sense is that? It would be sight, because you look at something and you estimate its size. A meter stick would be able to let you measure that and be sure of what you're talking about. But that would be extending your sense of sight. So now let's talk about measurements. Measurements and the units of measurements. A measurement is a direct comparison with a known standard. For example, that meter stick I'm talking about. This is a meter. If I hold my hands out like that, that is a meter. Okay? And so if I have something that is 4 of these, it would be 4 meters long. That would be a measurement of distance. This is a liter. It's 1,000 milliliters, which equals a liter. So if I fill this up, I know that that is a liter. Okay? Here is a kilogram. This mass has a mass of 1 kilogram, 1,000 grams. So we use certain standards, and we're comparing something to these standards. As long as you and I are using the same standard, we're going to come up with the same measurements. That becomes really important. If you're using a different size meter than I am, we can't talk. We can't work anything out in terms of measurements. So all measurements have 2 components. That specific unit that we're talking about, whether it's a meter or a milliliter or a kilogram or whatever, and a number indicating how many of those units we have measured. For example, well, how far is it to Liberty? What unit would you use? Well, here in the United States, we'd probably use miles. And we would say it's maybe 20 miles from Lake Huntington to Liberty. How long till you graduate? Well, for most of you, it's a number of years. And that's the unit. And you might say, if you're in 9th grade, it's, well, 9th, 10th, 11th, 12th. So you have just about 3 years till you're in your graduating year. How much do you weigh? Here in the United States, that would be given as pounds. So pound is the unit, and you'd indicate how many of those pounds make up your weight. English and metric units. Well, I posted a video on Schoology about how goofy the English measurements are. But the English measurements are they're based on dead king body parts. The king used himself as a standard. So you have the foot, which is a foot. An inch is a thumb. Yard is the distance from your nose to your outstretched hand. That would be a yard. right? Not the most efficient measuring system. The metric system used by scientists, and most metric system measurements are based on water measurements. And the idea is if we have a cube of water, and that cube of water is 1 centimeter on a side, to make a cube of it, that's 1 cubic centimeter. And 1 cubic centimeter of water has a volume of 1 milliliter. And furthermore, if that water is as dense as it gets, which occurs at about 4 degrees Celsius, that water has a mass of 1 gram. So you can see this is kind of a brilliant system. So we have the basics of this system. Length is the meter, volume is the liter, time is the second, your normal second, the mass is a gram. Derived would be combinations of basic units. Like, for example, velocity combined distance and time. When you talk about miles per hour, that's how many miles you went in an hour. So observations are direct interactions with our senses. Inferences are a scientific conclusion based on observations and experience, something that is thought out but not observed. For example, if you say the coffee has mist coming off of it, well, that's an observation. You're seeing this mist come off the coffee. If you say the coffee has just been poured, perhaps you're observing there's mist coming off the coffee, and so you're thinking that it's still very hot coffee, which means it's just been poured. But that, correct as it may be, is still an inference based on the fact that you're seeing the mist coming off the coffee. So most scientific facts are simply well-supported inferences. And we work those inferences and we try to think of any alternate explanations. We test them and see, are our inferences as correct as we can make them? So, inference or observation? Let's try it. It's hot outside. Check outside, seems hot. Is that an inference or an observation? Well, you go outside, you're testing it. That's an observation. Tomorrow will be hot. Well, it's not tomorrow. All we're doing is we're saying, based on everything we see right now, we believe it's going to be hot. That is an inference based on certain observations. Jim is limping. I look over, I see Jim limping. That's an observation. Jim hurt his leg. That's what I'm thinking because he's limping. So that would be an inference. The dog is mean. Well, you don't really see mean. You have observations that lead you to the conclusion that the dog is mean. What would one of those observations be? Well, how about the dog is growling? That would be a pretty reasonable observation, certainly an observation that would lead you to the inference that the dog could be mean. The light bulb is blown out. Right? We believe the light bulb is not working. Okay, there may be other things going on, but why do we believe that? That's an inference. Why do we believe that inference? Well, because the light bulb is not turning on. That's an observation. You flip the switch, light bulb's not turning on. That's my observation. And I might think that the light bulb is blown out. Hey, the electricity could be out. And the light bulb works fine if I could get electricity to it. The sock is white. That's an observation. The rock is 250 million years old. How about that? That is an inference. You weren't there, so we're doing a variety of tests and believing the rock is 250 million years old. Salt is bad for you. What do you think about that? Well, we see a bunch of observations that suggest that salt might not be the best thing you want inside your body in large quantities, and we're talking large quantities, so we would say salt is bad for you. That's an inference. Let's talk about scientific notation. Scientists work with very large and very small numbers. So to make this easier, we convert the numbers to something called scientific notation. So all the numbers are expressed with a digit, followed by a decimal point, and raised by 10 to some power. To do this, we move the decimal to the left in large numbers and to the right in small numbers. When moving the decimal point left in a large number, we just count how many jumps until it follows the first digit. The number of jumps is the exponent. So, 235,789, the decimal point is right there. How many jumps? We go 1, 2, 3, 4, 5 jumps. So we have 2.35789 times 10 to the 5th meters. And recognize we have the decimal after, right after the first non-zero number. 468 million. Well, we can jump in groups of 3 here. 3, 6, 7, 8. So it would be 4.68 times 10 to the 8th. When moving the decimal point right in a small number, we again count how many jumps until it follows the first non-zero digit. The number of jumps is the exponent, but now the exponent is negative. For example, 0.002357, yada, yada. All right, so we take the decimal point and we move it to the right. 1, 2, 3. And now it's following the 2. So we would say 2.35789 times 10 to the 3rd, to the negative 3rd. There'd be a little negative here that you can't see. All right, how about this one? Well, just grab the decimal point and start moving. 1, 2, 3, 4, 5, 6. So you get 4.61 times 10 to the negative 6th. Another thing we use a lot in earth science and in all the sciences would be something called percent error. How tall are you? If you were asked this, you'd give some answer in feet or inches. Are you correct? Exactly correct. Obviously, you're not exactly dead on perfectly correct. Every measurement contains some amount of error. Percent error tells us how far a measurement is from some accepted value. To calculate this, take the difference from the accepted value and divide by the accepted value. Multiply this number, it'll be less than 1, by 100. And at the end, place the percent sign. Please don't ever use the percent sign on the calculator. You can hit a percent sign, and that does another calculation. You will not come up with the right answer. So first, find the formula in your reference tables. When you're going to do one of these problems, very often they're full credit problems. They're worth at least 2 points on like the Regents exam. So the first thing you have to do, and it tells you this, write down the formula. So take the formula exactly the way it is on the reference tables, write it down, substitute the numbers you have with the units into that formula, and then go ahead and solve. That's how you get those full 2 points. But if you just solve it and give the answer, that's only one of those 2 points. That's 50%. So example, a student takes a stick, measures a stick to be 3.2 centimeters. The teacher measured the stick to be 3.4 centimeters. What is the percent error in this case? What is the percent error in this case? Well, the answer I've given is 5.9%. How do you do that? Well, you first write the formula. Percent error equals difference from accepted value divided by accepted value, okay, times 100. So what's the difference from accepted value? Well, 3.4 centimeters minus 3.2 centimeters is 0.2 centimeters divided by what? Well, divided by the accepted value, which would be the teacher value. So divided by 3.4 centimeters, press equals, that's a very tiny number, and multiply by 100. That gives you approximately 5.9%. Just put the percent in right at the end. A runner measured his sprint as 7 seconds. The official clock said 6.4 seconds. Okay, write down the formula. Percent error equals difference from accepted value divided by accepted value, and then substitute in. So the difference would be 7 seconds minus 6.4 seconds. That's 0.6 seconds divided by the official value. That's your clock, which is divided by then 6.4. Press equals, tiny number, multiply it by 100 equals 9.4. Put a percent there, so 9.4%. You weigh your cat to be 5.3 pounds, but the vet said 5.7 pounds. Okay? Percent error equals difference from accepted value divided by accepted value. Now substitute in. The difference would be 5.7 pounds minus your 5.3 pounds, or 0.4 pounds divided by, what's the accepted value? Well, the vet said 5.7. We'd have to think the vet is more correct. So divided by 5.7 equals, it's a tiny number. What do? Multiply by 100, put a percent sign at the end, and we get 7%. Okay, you guessed a pool to have 4,000 gallons, but the factory said it was 9,500 gallons. Factory is certainly more correct. So how do you do it? Percent error equals difference from accepted value divided by accepted value. So what's the difference? 9,500 gallons. And if you're ever in question, just do the math here. 9,500 minus 4,000. Well, what does that equal? 5,500. That's your difference from accepted value. You divide it by accepted value. Press equals. Okay. Multiply by 100, and you have about 58%. That would be the difference from the accepted value. You can see that's quite a large one. You could see that right in the problem. 58% is a long way away from the accepted value. So percent error tells you how good you got a particular problem, how close to the accepted value you were.